Use the integral test to determine convergence or divergence of the series. Integral test means that you write down this function and instead of summation you use an integral and you integrate by n and you use the same value for 2 to infinity. And the theorem is that if this gives you some convergent value, then this series converges. If this gives you some divergent value, if this goes to infinity or it does not exist, then this series also diverges. Now I usually like to just use x instead of n, so let me try to rewrite this. X ln of x cubed dx. And since ln of x looks like a nested function, I'm going to use u equal to ln of x to integrate this, which gives you du equals to 1 over x dx. Therefore, if you solve for dx, if you multiply by x, it's x du. And also when x is 2, u is ln of 2, and when x is infinity, u should also be ln of infinity, which is infinity. So therefore this integral becomes integral from ln of 2 to infinity. These are the values of u. 1 over x, we decide to replace ln of x by u, so you have u to the third power, and then dx is x times du. That's what we have here. And then these x's are a concern, but then since you have x and x canceling each other, you end up with this integral ln of 2 to infinity 1 over u cubed du, which is integral of u to the negative 3 du ln of 2 to infinity, and the integral of that is u of negative 2. You add 1 to negative 3, and you put the reciprocal of this number, which is negative 1/2, and you plug in infinity of ln of 2. Now, since u to the negative 2 is 1 over u squared, and there's a 1/2 multiplied, this is same as negative 1 over 2u squared, and it's a good idea to change it to this format because now it's clear what would happen if you plug in infinity into u. That's negative 1 over infinity minus negative 1 over 2 times ln of 2 squared. And notice that ln of 2 is some finite value, and therefore this is some finite value. You're subtracting. What about this? This is 0. So you have 0, negative is plus 1 over 2 ln of 2 squared. That's a finite value, so this converges. And therefore the conclusion, actually this is pretty important, you have to say, thus series converges by integral test. Let me try the second question. Now the second question is integral from 1 through infinity of x over square root of x squared plus 1 dx. And then since x squared plus 1 looks like a nested function, let's rewrite this as u. Du would be then 2x dx. And then when x is 1, u would be 1 squared plus 1, which is 2. So you're going to get the value of 2 for u when x is 1. And when x is infinity, u would also be infinity. If x over square root of u times, well, dx would be 1 over 2x times du So I put that in there, 1 over 2x times du, and these two cancel each other, which gives you the integral from 2 to infinity of 1 over square root of u is u to the negative 1/2 power times 1/2 times du, and then the power rule says you add 1 to negative 1/2, which is positive 1/2. Put the reciprocal in front, it's just 2 over 1, but then there's a 1/2 here, and then they cancel. And you plug in infinity into. Well, this is square root of u, so you're plugging infinity into here, which is square root of infinity minus square root of 2, and that's infinity. Since this diverges, we know that the series diverges by integral test. So that's the answer, and you do have to show all of this work. Use the alternating series test or absolute convergence test to determine convergence or divergence of the series. If the series converges, state whether it converges absolutely or converges conditionally. Well, if you have the absolute value of a sequence, and if this happens to converge, then we say that the original sequence, the one that had this alternating sign, converges absolutely. See, this negative 1 to the nth power, this will be equal to negative 1 if n is odd, and it would be positive 1 if n is even. So this will change between negative 1 and 1 depending on whether n is even or odd. So this has the property of making the signs alternate between plus and minus. So that's why we call this an alternating series. For alternating series, if you take the absolute value, you're going to basically be getting rid of this changing sign. So you're going to get n equals to 1 through infinity of 1 over 2n plus 1 factorial. Now, if this converges, we say that the original series converges absolutely, and there are some theorems out there which says absolute convergence is better than just this converging. So let's see how we can verify this converges or not. Well, you know, when you have a factorial, the test that you should use is the ratio test, which says it should be an, the original series an, and then 1 over 2n plus 1 factorial. This is a of n plus 1. So this one here is a of n plus 1. So n is replaced by n plus 1, and you take n to infinity. If this value becomes less than 1, if the absolute value of this is less than 1, then the ratio test says it converges. If it's bigger than 1, it diverges. If it's equal to 1, then we have to do something else. Okay, let's proceed. This thing here flips because you're dividing by a fraction, so it flips as 2n plus 1 factorial over 1 times this one here. It would be 1 over, and if you expand, this is 2n plus 2 plus 1, so it's 2n plus 3 factorial, and you're sending n to infinity, which is 2n plus 1 factorial over 2n plus 3 factorial. Now, what's a factorial? Factorial means you start from 1 and then 2, 3, all the way up till 2n plus 1. You multiply everything. Whereas 2n plus 3 factorial would be the same thing. You start from 1 times 2 times 3 times all the way up to 2n plus 1 and 2n plus 2 and 2n plus 3. You stop at 2n plus 3. And since this much, these are common, you end up with the limit n going to infinity of 1 over 2n plus 2 times 2n plus 3. And when the denominator n is sent to infinity, the denominator becomes infinity, so you have 1 over infinity, which is 0. Now, because 0 absolute value is less than 1, that means series converges. This series converges, and then therefore the original series does converge absolutely. So series converges absolutely by the ratio test. Now this one here, if you take the absolute value to get rid of this negative 1 and just write down square root of n over n plus 1. Now see that square root of n is 1/2 power, and this n is like n to the first power, and this n is the dominating term. This is much bigger than 1 when n goes to infinity. When n is like a million, million plus 1 is pretty much the same thing as just million itself. So you can just think of n as n plus 1 as something similar to n. And so what I'm trying to say is that square root of n over n plus 1, when n is really large, this is pretty much the same thing as n to the 1/2 power over n to the first power. You can ignore 1 when n is really large. Now, you also know that you can subtract if you're dividing, so you can subtract the exponents. So this is 1/2 minus 1, which is n to the negative 1/2, which is like 1 over square root of n. Or I think it's better to say n to the 1/2. So what this is telling us is that this series will behave pretty much like n from 1 through infinity of 1 over square root of n, or n to the 1/2 power. But what is this? This is the p series with p equals to 1/2, and since that's 1 or less, we know that this diverges by p-test. Okay, so therefore we can conclude that this does diverge. So that's like a very rough way to say what's happening. To really argue what this approximately equal mean, you shouldn't be really writing this. Rather, you want to write something like, you can just erase everything here. That's not needed. All you have to write is that, yeah, let me rewrite over here. But that process I just deleted, this is really important. You have to be able to think this way, or else you wouldn't be able to write down what I'm writing now. So first you say sigma of n equals to 1 through infinity of 1 over square root of n, which is sigma n from 1 through infinity of 1 over n to the 1/2, diverges by p-test, where p is equal to 1/2, and that's 1 or less. Okay, if the p-value is 1 or less, then we know that the p-test says this thing diverges. And then in order to compare these two, what you use is you use the limit comparison test, which says if you take the ratio between the two series, here's one series and the other series is 1 over square root of n, right? And if you flip the denominator, change this division to multiplication and flip, change, flip. So you get this, which is like limit n going to infinity of square root of n times square root of n is just n. So when you take n to infinity, this becomes 1. And the important thing is not the value. The important thing is that it's a finite number which is not equal to 0. Which means by limit comparison test, is sigma square root of n plus square root of n over n plus 1 diverges. So the original series cannot converge absolutely. So this original series, which was -1 to the n plus 1, sorry, this one, right? We're doing this one. Square root of n over n plus 1. This does not converge absolutely. Now, that doesn't mean that this could converge conditionally. And to do that, you need to do some more work, which is called the alternating series test. Okay. So what is the alternating series test? Alternating series test does the following. Okay. The alternating series test does the following. You have to first denote AN, the part that's not alternating, only just this part. And you have to show two things. That first, limit of n going to infinity of square root of n over n plus 1 gives you 0. Which is just basically true. If you are not so sure, another way to show that this is true would be to use the L'Hopital's, because this is infinity over infinity. So if you differentiate the top, it's 1 over 2 radical n. If you differentiate the bottom, it's just 1. And since n is taken to infinity, this would be 2 times square root of infinity, which is just 1 over infinity, which is 0. Okay, so limit of an is equal to 0. That portion is checked. The second part that you do have to show is that an is greater or equal to an plus 1. Now, this doesn't have to be true in the beginning. You may have a few of the first terms to violate this, but then after some point, as long as this does hold true, then the alternating series test works. And by working, I mean that it gives you the conclusion that the series does converge conditionally. Now, however, if you write down an as this and an plus 1 as n plus 1 over n plus 1 plus 1, it's extremely hard to show why this would be bigger than that one. Okay. So often, the hardest part of figuring out that something converges by an alternating series test would be to show this inequality. However, since showing the inequality is hard, the easier way would be just to simply differentiate this thing and show that its derivative is negative. Because if its derivative is negative, that means you know that it's a decreasing function. And when this inequality that an is greater or equal to an plus 1 basically means that the sequence an is decreasing. So we differentiate this using the quotient rule. Minus square root of n over n plus 1. And this becomes, let's see, 1/2 square root of n. So if you simplify, it will be 1/2 square root of n, and then plus 1 over 2 radical n, and then n plus 1. And the thing is, if n is 1, this would be 0, but if n is 2 or greater, this would be negative, because this will be a decimal, whereas if this is well, I guess when n is 4 or greater, that would mean that negative 1/2 square root of n is negative 1 if n is 4, so it will actually be less or equal to negative 1. So for example, if n is 9, it would give you negative 3 over 2, so it's definitely less than negative 1. And because of this, the top one would be less than 0, because this is just a decimal value when n is 4 or greater. So you have negative 1 plus a decimal, which is still negative, right? So this would mean that the derivative of square root of n plus 1, square root of n over n plus 1 prime, is less than 0. So we do know that an is greater or equal to an plus 1. Check. Therefore, by alternating series test, the series converges. Determine the convergence of the series. Let's try this one. Now, none of these are alternating, so you have to use other tests like p-test. Then you have the limit comparison, direct comparison, and you also have the ratio and root test, sometimes called radical test, because taking roots are taking radical powers. And these actually would require something like some constant to some nth power. If you see something like this, you would be thinking of either the root or ratio. And in most cases, unless it's plainly just screaming for the root test, usually you just use the ratio test and it works. If you have a to the n, it will usually work if you do have the ratio test. And another thing is, if you have n factorial, you definitely want to use the ratio test. But if you don't have n factorial or something to the nth power, then that means you just have to figure out by using these. And a is such a thing, right? Now, though you don't have to write this, it's very helpful if you try to figure out what kind of function this is. When n is really large, this will be similar to 3n over n squared, which is 3 over n. And so adding this would be same as adding these, but sum of 3 over n, we know that that's a harmonic series. Or another way to say it would be that this is a p-series, 3 times square root of 1 over n equals to 1 through infinity. And since p is equal to 1, that means this diverges. Okay, now how do you make this actually turn this into an actual solution? Well, this is how you roughly argue, but that's not the full solution. To correctly argue, you need to use either the limit comparison test or direct comparison test. Usually direct comparison test is hard, so you just want to stick to limit comparison test if you can. So let's try that. We use the limit comparison, n going to infinity, of this 3n minus 2 over n squared plus 5 to this other number that we just figured out, which is 1 over n. And the limit comparison test basically says that if this gives you some non-zero value, then the series of this will converge if this converges, if this will diverge if this diverges. Okay, so that's how these two things will be related once you can show that you get a non-zero number. Okay, we use the keep, change, flip method again. So keep this much, you change the division into multiplication, and you flip 1 over n, which is n over 1. So that gives you limit n going to infinity of 3n squared minus 2n, because n is multiplied to the top, and 1 is multiplied to n squared plus 5, so this is what you get. And when you do this, you see that 3n squared and n squared, these are the dominant terms. 3n squared is much bigger than negative 2n on the top, so 3n squared is a dominant term on the top. N squared is much bigger than 5, so n squared is the dominant term on the bottom. So this limit would be same as limit of 3n squared over n squared. N squared and n squared cancels and you get 3, which is not equal to 0. And since 3 is not equal to 0, we can now say since summation of 1 over n to infinity diverges by p-test, and in our case p is 1 and it does satisfy 1 or less, the inequality that 1 is 1 or less, so in this case we can deduce that it diverges. And since we just have shown that these two are comparable, now we have the summation of n from 1 through infinity of 3n minus 2 over n squared plus 5 diverges by limit comparison test. The important thing here is that you have to know how to figure this out. So you should know several things. I mean, what if you had something like, instead of this, if you had like 3n minus 2 with a square root over n squared plus 5, what would you do? Well, in that case, you would do square root of n would be the dominant thing on the top, and n squared is on the bottom. And since this is 1/2 power and this is n squared, this will be same as 1 over n to 3 over 2. And if you're adding this, we know that this converges because p equals to 3 over 2 is bigger than 1. So being able to do calculations like this is very essential in knowing what to choose for the limit comparison test. Now the second question, I see a factorial, so we use the ratio test, which says limit n going to infinity, and then you have e to the n over n factorial, and on the top you replace n by n plus 1, so that gives you limit n going to infinity of e to the n plus 1 over n plus 1 factorial times n factorial divided by e to the n. And that one is n factorial over n plus 1 factorial times e to the n plus 1 divided by e to the n, limit n going to infinity. This one is 1 times 2 times all the way up till n. This one, n plus 1 factorial, will be 1 times 2 times n times 3 times all the way up to n, but then it has to end at n plus 1. Basically what I'm trying to say is that these are common, so they're going to cancel away, leaving behind just n plus 1 after cancellation. And this one, since e to the n plus 1 is same as e to the n times e to the first power, when you divide this by e to the n, you end up with just e by itself. So that gives you e over infinity, which is 0. Now what's 0? 0 is less than 1, so series converges. This series here converges by ratio test. Here I have 3 to the nth, 8 to the nth, 7 to the nth, and if it was like 3 plus something n and 7 to the 7, and then you had n overall, then you would use the root test 1 over n. However, here none of that is true. What we're given is that you have 3 to the n, 8 to the n, and 7 to the n is given to us individually, in that case, taking the nth root is not going to do any good. So in this case, it's better if you do ratio test. Okay, so we're going to do the ratio test, which says r is equal to limit n going to infinity of, in the denominator you have 3 to the n plus 8 to the n over 7 to the n. On the top you have 3 to the n plus 1 plus 8 to the n plus 1 divided by 7 to the n plus 1. And then when you simplify, you have, when you flip this, you have 3n plus 1 plus 8 to the n plus 1 over 7 to the n plus 1 times 7 to the n divided by 3 to the n plus 8 to the n. What I did was I just flipped the denominator and put it here. Now what is this? Since this denominator is 7 to the n times 7, 7 to the n will cancel out and just leave 1 over 7 behind. What about these two? Well, if you look at the top, 8 to some power is much bigger than 3 to some power. So for example, when n is, say, 1, which is 8 squared, that's 64, whereas 3 squared, that's not 9, just 9. So this will increase to infinity much faster, meaning that this will be the dominant term. Same thing with the denominator, this will be the dominating term. And so what you say is that this is going to be limit n going to infinity of 8 to the n plus 1 over 8 to the n. Remember there's a 1 over 7 before, and since these two will cancel out and leave you with 8 over 7 as your r value, and 8 over 7 is definitely bigger than 1, in that case we know that the series diverges by ratio test. Okay, so that's how you solve this part C. Okay, now we have part D, where I have to figure out what to compare this with. See, sine of x, the Maclaurin series of sine of x is x minus 1 over 3 factorial x cubed, and so on and so on. So if you just choose x, x is indeed very close to sine of x. For example, if you have x as 0.1, this value will be very close to 0.1, because if you plug in 0.1 here, you get 0.1, then you subtract a little, but that's a very tiny amount, because 0.1 cubed is 1,000th, and this is a 6, so this is 1 out of 6,000, very small value. So you get some really tiny quantity, and then you add something afterwards. What I'm trying to say here is that if you evaluate sine of some value which is close to 0, the outcome of that would be some value very similar to what you have here. So you can even check this by using a calculator. If you do sine of 0.1, you're probably going to get something like 0.0999 something. So that's very close to 0.1. So that's what I mean. Now, why am I trying to explain this in detail? That's because when you see n times sine of 1 over n cubed, you should really think of this as n times, since I said sine of x is similar to x, sine of 1 over n cubed, it will be similar to 1 over n cubed. And that would be 1 over n squared. And so what you see is that this can be comparable to sum of 1 over n squared. But what do we know about 1 over n squared? This is a p-series with n equals to 2, so this thing converges. Okay, so that's what you want to say. Okay, so far this much was just thinking out loud phase. And none of these should be included in the actual solution. The actual solution goes like this. Solution is first sigma 1 over n squared converges by p-test, because p is equal to 2, which is bigger than 1. And then what we want to do is to take the limit comparison test of n times sine of 1 over n cubed with 1 over n squared, and that gives you limit n going to infinity of n cubed, because this flips over and you get n squared over 1. N squared times n is n cubed, and sine of 1 over n cubed. Oh, that's interesting. 1 over n cubed can be replaced by t, with t is sent to be 1 over n cubed. Then the limit as n goes to infinity can be replaced by as t goes to 0 plus. That's because n cubed is 1 over t, and therefore when t becomes very, very small, 0.001 or something like that, then n becomes big. So sending n to infinity would mean that t is sent to 0 plus. And then, so this we decide to call it as t, and we also know that n cubed is 1 over t, so we have sine t over t dt, no, limit, this is limit. And what's the limit of sine of x over x? We learned that this is equal to 1, right? So that's very helpful, because now we have a non-zero value. If you get a non-zero value, then it means that these two things are comparable, and since the original thing does converge, we know that series converges by limit comparison test. Okay, this last one here, this one has 3n squared. In that case, it would be nice to take this function, the sequence, and take the 1 over nth power, which means I'm trying to do the root test. Okay, so you want to do the root test, and since these two multiply, you get 3n here, 1 plus 1 over n, and limit n goes to infinity. Now this is another challenging limit. So you devise another plan. You set x as 1 over n, which means n would be 1 over x. So this would be equal to limit n going to infinity of 1 plus x to the 3 times 1 over n, because 1 over x, because n is 1 over x, so I can replace n by 1 over x. Now why do we want this? That's because we can rewrite this as e, limit of n going to, actually sorry, this would be limit of x going to 0 plus, since if n is infinity, 1 over infinity is 0, so x would go to 0 plus, of e of ln of whatever you have here, which is 1 plus x cubed times 1 over x, so it's 3 over x. And then 3 over x can be pulled outside. It can jump over the log, which gives me the limit x going to 0 plus of e of 3 ln of 1 plus x divided by x. Now since this one, when you send x to 0, this looks like a 0 over 0 type, therefore you are allowed to use the L'Hopital's, which says that when x is sent to 0 plus, this will be e to the derivative of this, which is 3 over 1 plus x, and the denominator, when you differentiate x, it will be 1. So this is all you have, which is e cubed. Now e is about 2.7, so if you take 2.7 to the third power, e to the third power is definitely bigger than 1. That means series diverges. If it's bigger than 1, it diverges by root test. Okay. What is the error bound of S of 99 of this sum? Well, if you have a partial sum, if you have the difference between the approximation to the actual value, this is what we call the error. Error would be the actual value minus the one that you estimated, and the error between the two would be determined by the next one, which is a of 100. And by a I mean the this term here. We are trying to call an as -1 to the n plus 1 over 2n squared. By the way, this is only true for alternating series. Okay, so alternating series says that if you have some partial sum, if it stopped at the 99th term, then the difference between the actual and the 99th term approximation depends on the next term in the series. So the difference would be less or equal to 800, and because a of n is this thing, what is a of 100? A of 100 would be just plug in 100 here, right? By the way, sometimes if it's negative, then you should put a positive one. So if you have -1 to the 100th power and you add 1, that's 101, divided by 2 times 100 squared. And since this is negative, when you take the absolute value of this, you're going to get rid of this -1, and you end up with 1 over 20000. So that's the maximum error. This is the error bound. Error bound. Error bound. Okay. So that was actually a very simple question. Find the interval of convergence and radius of convergence of the following power series. Very important formula, because these type of questions tell you when you can use the Maclaurin series or Taylor series you just obtained. So this is a very important question here. To get the interval, what you want to do is always start out by using the ratio test. So you have 3 to the n over 2n plus 1 and x minus 1 to the m. That's just, I'm just copying this much here, right? And on the top, you replace all the n that you had down here as n plus 1. Sorry, this is n. And then over 2 times n plus 1, and then x minus 1 to the n plus 1. I guess the easiest one is this. If you cancel out the x minus 1s, this has n of them, this is one more than the bottom. So when everything's cancelled, you end up with x minus 1 on the top. Now these two, you can flip this by using keep change flip. I forgot to extend n to infinity. Limit n going to infinity. This would be, you have 3 to the n plus 1 over 3 to the n, and then 2n plus 1 would be on the top because you flipped. This becomes in the numerator, and the denominator is 2n plus 3. Now what's the limit? We know that this gives you 3, and this will become 1 because 2n and 2n are comparable when n is really large, and you have the first power, x minus 1 to the first power. So you end up with 3 times 1 times x minus 1. So it's 3x minus 1. Now what do we do with this? We have to use, since this is a ratio test, we have to use the fact that the ratio test will give us convergence only when your r value is between -1 and 1. So we have to solve this. Divide by 3, you get x minus 1 less than 1/3, and also less than -1/3. And then finally, when you add 1 both sides, you end up with 2/3 and then 4/3. Okay, so we have several things to do now. We first need to figure out the radius of convergence, if this is given, so radius of convergence would be to take the two values, so 4/3 minus 2/3, and then divide this by 2, so that's 2/3 divided by 2, which is 1/3. Okay, so that, since the interval that we have is like from 2/3 to 4/3, the radius of this would be just this minus that divided by 2. That's what I'm doing here. So that's the radius of convergence. So radius of convergence, this would be 1/3. Okay, but that's not all. You still have to find out what happens at the boundaries, because ratio test is notorious for the boundary cases. You don't know what's going to happen at the boundary, so you have to check the convergence at each endpoints. So let's try to check what happens when x is equal to 2/3. In that case, this will be sigma n from 0 to infinity of 3 to the n over 2n plus 1. 2/3 minus 1 will be negative 1/3. And because this negative will make the signs alternate, I want to take that out. Negative 1 to the nth power times, you have 1 over 3 to the n, or 1 to the n is 1, 3 to the n. 3 to the n will cancel each other, and then you end up with sigma of n from 0 to infinity of negative 1 to the nth power 1 over 2n plus 1. So that's what you get if x is 2/3. But what does this do? This actually makes this alternating thing makes this convergent, because limit of 1 over 2n plus 1 does give you 0. That's the first condition you have to check for alternating series test. It's made up of two things, right? This is 1, and then 2, you have to know that this is a decreasing sequence, that this an is less or bigger or equal to 1 over 2 times n plus 1 plus 1. So the next term is always smaller than the previous one, and that's obviously true because the denominator is bigger than the previous one. Since these two conditions are met, we know that this is convergent conditionally, but all we want to know is whether it converges or not. So whether it converges conditionally or converges absolutely, it doesn't really matter to us. All we care is about convergence itself. So it converges. Now what if you have x equals to 4/3? In that case, 4/3 minus 1 gives you 1/3, so you have sigma n from 0 to infinity of 3 to the n over 2n plus 1, 1/3 to the nth power. And since 1/3 is reciprocal of 3, these two are going to cancel, and you end up with sigma of 1 over 2n plus 1. And that's harmonic series. We call some constant over another constant plus another constant. This is called the harmonic series. And in that case, it always diverges. So it diverges. Okay, so we knew that between these two numbers, this series converges. But now we also know that 2/3 itself is convergent, whereas 4/3 will make it not convergent. So that's your this will be your interval of convergence. And we did do the radius of convergence of this interval, which is subtract the 2 and divide by 2. Radius would be 1/3. Okay, find the Maclaurin series of the following functions in sig notation. Okay, so if you have log log of x plus 1. Well, first of all, let's think about what Maclaurin series formula is. Maclaurin series formula says that f of x is equal to f of 0 plus f prime of 0 over 1 factorial x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, and so on and so on. This is the formula. And in theory, it could work. If you're patient enough and you can find the pattern, it could work. So let me show how this one works. ln of absolute value of x plus 1. When you plug in x equal to 0, so that we evaluate f of 0, that gives you ln of 0 plus 1, which is just ln of 1. What is ln of 1? That's 0. So we know that this very first one is 0. Now you differentiate this, so ln of x plus 1 has to be differentiated, and you have to plug in 0 afterwards. Differentiating this gives you 1 over x plus 1, right? And you plug in 0, so you get 1. And then you do another one, you do the second derivative, and then plug in 0. That means you're differentiating this, which is negative 1 over x plus 1 squared. And you plug in x equals 0, that gives you negative 1. And then you differentiate. I think if you're trying to do it this way, you'll have to end up differentiating probably something like 5 times or 4 times. You have to be patient, but you know, final exams are often long, and you may still have time to do all that derivative. Okay, if you differentiate this, which means you're differentiating this, since this is x plus 1 to the negative 2 power, negative 2 will come down and give you positive 2 and x plus 1 cubed, and therefore when you plug in 0 you get positive 2. And if you differentiate yet again 4 times and plug in 0, then this negative 3 is going to come down and you get negative 3 times 2, and then 1 over x plus 1 to the 4th power, and when you plug in 0 you get negative 3 times 2. So it looks like 3 times 2, the next one will be 4 times 3 times 2. So it has the look of like n factorial, and there's this alternating sign somewhere. So this seems to be what's going on. Starting from n equals to, let's see, when n is 1, this gives you, oh, I should alter this. Okay, so when is 1, when n is 1, this does give you that, and when n is, oh, I see, 3 gives you 2, 4 gives you 3, so actually what you want to do is not n factorial, it's n minus 1 factorial. Okay, so let's do n. When n is 1, you get, okay, so after a bunch of trial and error, I got this as my f differentiated n times plugged in 0. And if you know this, then you can plug it in here and get some result, and that will be one way to do it. Now, however, if you don't have that much time and you want to get the result quickly, then you have to be a little more smart about what the relationship between what you're given to what you know are. So, for example, if you have ln of absolute value of x plus 1, think about the derivative of this, which is 1 over x plus 1, right? But this 1 over x plus 1 is very similar to 1 over 1 plus x. I mean, they are equal because addition is commutative. And then since this is same as 1 over 1 minus negative x, you can basically use this formula here, but replace x by negative x. So that gives you 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th and so on and so on. Therefore, what is ln of x plus 1 itself? That would be the integral of this. So 1 integrates to x integrates to 1fx squared, and x squared integrates to 1/3 x cubed, negative 1/4 of x to the 4th, 1/5 of x to the 5th, and so on and so on. And then you want to write this in a sigma notation. Sigma notation says that the power here starts from 1 to infinity, so you have x to the n, and there's a change in the sign, so negative 1 to the n minus 1. When n is 1, it's positive. When n is 2, it gives you negative, so you need n minus 1 to get the correct signs match. And then whenever you have an n here, then 1 over n is in front, so this is what you get. So that's the this one is the Maclaurin series of this function. Okay, so if you kind of stop for a moment and see if these two things are related by some derivative or some other algebraic ways, then that's very convenient. Now let me show you how you can do this one here. That one, well, this is 1 over 1 minus negative x squared, so this again can be solved, negative x squared. This can again be solved by using this one, which is that 1 plus negative x squared plus negative x squared squared negative x squared cubed, and so on, right? Or you can even put it in here, which is sigma n from 0 to infinity of x to the n, but negative x squared is replacing x, so you get sigma of n from 0 to infinity of negative 1 to the nth power and x to the 2nth power. Now what about x times sine 3x? For x times sine 3x, you use the sine x series, which is this, and then you have sine of 3x would be summation of n equals to 0 to infinity of negative 1 to the nth power 2n plus 1 factorial and x to the 2n plus 1. But instead of x, you have 3x, so 3 should go in here, which means that you have sigma n equals to 0 to infinity of negative 1 to the nth power 3 to the 2n plus 1 over 2n plus 1 factorial times x to the 2n plus 1. And then now you think about what happens to x times sine 3x. That would mean you multiply x to what you already have, okay, and then if you multiply this to inside, then you have x to the first power and x to the 2n plus 1 power, so the final answer will be from 0 to infinity of negative 1 to the nth, 3 to the 2n plus 1 over 2n plus 1 factorial, and this would be x to the 2n plus 2, because 1 plus 2n plus 1 is 2n plus 2. So that way you can kind of avoid having to use the formula for Maclaurin series. Yeah. There are times when it's inevitable, you really have to use the formula, but okay, Taylor series. Taylor series is a modification of, or generalization of, the Maclaurin series. And the formula looks pretty much the same. F of x is f of c plus f prime of c over 1 factorial x minus c. The only difference is you have to plug in c instead of 0, and instead of x, you need x minus c at each stage. But you're going to see the similarities so on and so on. Now, if you say you want a Taylor series given to the given order n, so to n equals to 2, that's the power here, that's your n. So for a, you would just stop at the third one. If n is 2, you're going to use these 3. And in practice, that often happens because you don't need that many terms to have a good approximation. You may truncate the series. Depending on the series, sometimes you can just truncate the first 3 or first 4 and it's still good enough. So let's try this one. Since I need this, this, and this, I would need first and second derivative. Okay, so if I differentiate f of x, you have to differentiate using the product rule, which is e to the x plus x times e to the x. And it's a good idea to factor and simplify as much as possible before you get to the next stage, because you have to differentiate again. Second derivative is, again, the product rule. 1 plus x is differentiated times e to the x plus 1 plus x times e to the x prime, which gives you e to the x plus 1 plus x e to the x, which is 2 plus x e to the x. Okay, now that we have all the function, first derivative and second derivative, let's try to figure out the value at c equal to 1. We need f of c, f prime of c, and f double prime of c. So f of 1 is 1 times e to the first power, so it's just c. F prime of 1 is 1 plus 1 e to the 1, so it's 2e. See, you're plugging in 1 here, 1 there, so it's 2e. And f double prime of 1 would be plugging in 1 here, so it's 3 times e to the first power. Okay, so we have everything that we need. We know that x times e to the x is e plus 2e over 1 factorial x minus 1, c is 1, remember, plus 3e over 2 factorial x minus 1 squared. So this one would be our solution. Let's try the next one. You have f prime of x equals to negative sine of x. F double prime of x equals to negative cosine of x. F triple prime is equal to positive sine of x. And f triple prime would be associated with x minus pi over 3 to the third power, so that's when you stop. Now for these, let's evaluate. F prime of pi over 3 is negative sine of pi over 3, that's negative radical 3 over 2. F double prime of pi over 3 is negative cosine pi over 3, and that's equal to negative 1/2. F triple prime of pi over 3 is positive sine of pi over 3, which is radical 3 over 2. And we also need the original function at pi over 3, which gives you cosine pi over 3 plus 1. Cosine pi over 3 is 1/2. 1/2 plus 1 is 3 over 2. Okay, so what do we have now? We have the following series. Cosine of x plus 1 is similar to, because we're truncating, we have to say similar to. I think I did say that. Here you also have to say approximately if this is true. Okay, so here we have the value of pi over 3, which is 3 over 2, plus first derivative over 1 factorial times x minus pi over 3, plus negative 1/2 over 2 factorial x minus pi over 3 squared, and then plus radical 3 over 2 over 3 factorial x minus pi over 3 cubed. Okay, that would be order 3, centered at pi over